Okay, well, thank you very much, Jacob, for inviting me to talk here. What I'm going to talk about today is, well, a project that I've been working on for several years and never published anything on. There was a workshop back in Cambridge several years ago where I talked about a very early version of this, and it is now greatly improved, as I hope you'll see. So is the question about whether we should talk about retrocausality in quantum mechanics is the main issue at stake here. Okay, so the first sort of half of the talk or so will be sort of the philosophical part. I want to qualify it by saying I'm not a philosopher, and I'm definitely not a philosopher of causation. So some of the things I say will be very crude compared to what we heard from Holly just now. But I want to outline the motivations for thinking about retrocausality and talk about a way in which we can make sense of causality in a world which has potentially retrocausality. And then in the second half of the talk, I'm going to get into the technical details a bit, and I'm going to apply it specifically to the context of Bell inequality type of experiments, because that's the main context where this question has arisen. So I want to treat that case in general, and I'll say sort of some very short remarks about the case of general causal structures. Okay, so let's think about an experiment to test Bell's theorem. And here at the top, I've drawn the usual kind of structure of this. We have Alice and Bob here, who have their choices of measurement setting X and Y, and then they observe a measurement outcome A and B. And under the usual assumptions, that includes a lot, because I know there are very big debates about how to understand Bell's theorem in the literature, but so under the usual assumptions means all of that stuff, right? But Bell's theorem basically tells us that the predictions that quantum mechanics makes for these kinds of experiments when we prepare entangled states cannot be reproduced by a causal model which has the structure given in the diagram. So there's some common cause in the joint past of the two wings of the experiment that is responsible for the correlations between those two wings. I'm going to use a color coding in this talk. It's helpful for me. I don't know if it'll be helpful for everybody else, but there's going to be three types of variables we're going to consider. If something's in red, it means it's something that's under the direct control of an experimenter. So this will be something like the setting on a measurement device. The black variables are things that are only observed. They may be influenced by the things that they directly control, of course, but they're observed quantities like the measurement outcomes themselves. And then blue means some kind of hidden variable. I generally call these latent variables in the terminology of causal modeling, but there's something that's neither directly controlled nor directly observed. Okay, so we can't have this kind of causal model according to Bell's theorem. And one way of fixing this was proposed by Costa de Beauregard. This is the idea of the causal zigzag. So all we do is we take this arrow here and we turn it around the other way. Okay, so the idea is that the causal influence propagates along a zigzag path from Alice's wing of the experiment to Bob's wing of the experiment. So this was actually proposed by Beauregard in response to the EPR argument, Einstein, Podolsky, Rosen, before Bell's theorem. He proposed it in the 1940s. His PhD supervisor, Louis de Broglie, was not keen on him publishing it, so the proposal wasn't published until 1953. Hugh Price has talked about this history quite a lot, and you can find out more information about it in this paper that he wrote with Ken Wharton. Okay, so that's the idea, that we just turn this arrow around and we have a zigzag. And so why might we want to contemplate that? Well, it offers the possibility that all of the causal influences operate along time-like paths in space-time. Okay, so some of those paths operate backwards in time, but they're all operating within the light cones, as it were. So a theory that operates in this way, the thought is, might be easier to reconcile with Lorentz invariance than a theory that has explicit non-local superluminal influences. Okay, so that's one of the positives of the idea. However, I don't think that we can really take the zigzag literally. Okay, so in physics, at least, normally we think of things like, you know, causality and the arrow of time as some kind of an emergent macroscopic notion. Our fundamental laws are time symmetric. So if you have some kind of an isolated quantum system, it doesn't really have an arrow of time. It doesn't really have something like that. So if you think that the causal mediaries in this diagram are supposed to be the electrons or the photons that are being dealt with in your Bell experiment, the idea that the photon that's going from here to here actually has an arrow of time that could sort of turn around one way or the other is a little bit suspect. So instead of a zigzag, what I propose is more of a block universe type of model. Okay, so the idea here is that, you know, normally in physics we think about our physical theories in terms of some state which you may be able to attach to a space-like hypersurface, which then you can evolve forwards or backwards in time all at once. But the idea here is, let's think about the laws of physics as more like something like a jigsaw puzzle, right? So what goes on in one particular region is constrained in a symmetric way by what's going on in the neighboring regions. Okay, and we want to try and build up the laws like that. In particular, if the past can constrain something that happens in the future, then in this kind of framework, you could also symmetrically have what goes on in the future constrain what happens in the past in a symmetric way. Now, if you adopt this kind of framework, then, you know, in general, it would be possible to, you know, influence the past by changing what goes on now. Okay. In fact, we can't do that, right? So in fact, we can't send signals backwards in time, for instance. But the idea here is that the ability to influence the future but not the past would be explained in some kind of an emergent way, in the same sort of way as the arrow of time. You know, we currently need a thermodynamic account of the arrow of time. So whatever notion of thermodynamics is appropriate to formulate in this framework, and it is indeed not obvious, because normally when we're talking about thermodynamics, we account for the arrow of time in terms of special initial conditions, right? So here there's no privileged role for initial conditions, so it's not entirely clear what to do, but we need some notion like that. And the idea is that the ability to affect the future but not the past would be emergent from that in the same way as the arrow of time. That is an account that doesn't exist yet, but we're going to think about this sort of jigsaw puzzle block universe type of view. Okay, so let's look a little bit at the assumptions behind Bell's theorem. So there's the measurement independence assumption, right? So this is the the assumption that normally says that we don't have retrocausal influences. So it says that these hidden variables, or this latent variable, is uncorrelated with the measurement settings X and Y. Okay, so that's one of the assumptions. And then we have the actual locality assumption, which sort of screens off the two wings of the experiment given lambda. Okay, so what we're talking about here is that, in this kind of framework, in this kind of block universe framework, the measurement independence assumption is perhaps suspect. And this might allow us to get some kind of notion of locality still to happen in this framework. Of course, assumptions equivalent to measurement independence appear in almost all no-go theorems for realist models that underlie quantum mechanics. So, one of the reasons for considering this is that maybe we can get all sorts of properties of our model that we would really like, not just locality, but also perhaps evade assumptions about, evade theorems about contextuality or reality of the quantum state, etc., by dropping this assumption. Okay, so I'm not here advocating that this is definitely the way to go, but I think as a possibility, it deserves to be investigated thoroughly. Okay, so I also want to try and persuade you that I'm not completely crazy. This slide doesn't manage to do that because it just, if you think this idea is crazy, then it just shows you that there's a number of other people who are crazy as well. But the point is that there is sort of an increasing amount of work where people are proposing specific concrete models that violate the measurement independence assumption in some way and are able to reproduce various quantum phenomena. To my knowledge, there is not what I would call a complete account of the whole of quantum mechanics along these lines, at least not a compelling one, but there are various sort of toy models or models for specific scenarios. And I'm also not claiming that all of these models work exactly as the authors describe. There's a lot of controversy about this kind of area, but just to show that there is sort of increasing interest in it. Okay, so here's some questions that we should ask though. So if we're going to contemplate this kind of block universe model that violates measurement independence, then first of all, how should we think about causality in this kind of theory? Do the conventional notions work? And then, most of the work has been, as I've said, about building concrete models, but we need something more than that. We need a general framework which tells us what the structure of these models should be like. This is because, we want to think about things like, well, what do we even mean by locality in such a framework, right? It's all very well to propose a concrete model, but when we drop measurement independence, does that mean that we should think about modifying the other assumptions we use as well? So I'm going to argue that actually we should do that. And if you're trying to prove whether or not a no-go theorem holds, or you're trying to prove that a no-go theorem still does hold in this framework, for instance, then you need a framework at that level of generality. So that's what we're going to try and ultimately provide. Okay, so let's think a little bit about causality, measurement independence, and causality. So if we think about, probabilistic Reichenbach's principal notion of principle of common cause, Reichenbach would say that if there are correlations between lambda and x and y, then there are three possible kinds of explanation. So one is that lambda, the latent variable, influences these measurement choices. It causes these measurement choices. And this would at least rule out complete free choice, right? So what is apparently a free choice of the experimenter is actually predetermined and caused by the pre-existing hidden variables. The other way around, we could think of x and y as a cause of lambda. That's the retrocausality option. But there's also the option that they have a common cause. So perhaps somewhere in the past of the universe, there's something which correlates the hidden variables with our measurement choices. Okay, so this would be called superdeterminism. It also rules out free choice to some degree because that common cause in the past is now partly determining the measurement choices. So we know a lot more about causal modeling now than we have previously. It is possible, in Pearl type causality to distinguish these different kinds of causal arrangements, right? So, but in order to do that, in general, you need to do more than just observe what happens. You need to be able to make interventions. And, the point is that lambda variables are variables that we, by nature, cannot make interventions on, at least right now with current technology. So maybe at some point in the future, if we know more about a theory that underlies quantum mechanics, we could actually distinguish these, but to our present state of what we can actually do in the laboratory, we can't. So depending on what theory of causality you adopt, some of these might be actually not make sense, and I will argue that in a minute. But at least different theories of causality, what you mean by causality might affect your approach to building models in the scenario where we've dropped measurement independence. Okay, so I want to, well, okay, I'm going to say some things about causality here, which are probably going to be controversial, but at least I want to adopt this approach in this particular context. Okay, so I'm calling this the subjective-interventionist approach to causality. Hugh Price is the same as what Hugh Price calls the epistemic interventionist approach to causality, but I think it's actually a little bit more radical than just being epistemic. So the point is that it's sort of difficult to talk about cause and effect in a block universe model, right? So, you know, we have a 4-dimensional block, and whatever happens in that block just happens. So it doesn't seem like there's any kind of fundamental or ontological, if you like, notion of cause and effect going on here. I'm kind of sort of with Bertrand Russell on this point. In sort of the fundamental laws of physics, it just doesn't seem like there's any notion of causality. So also, you know, if we're adopting sort of a closest possible world semantics for counterfactuals to try and help identify causal relations, then it doesn't really work very well in this context, because, you know, normally we think about causes as being in the past and effects as being in the future, and we have no really good reason in this kind of framework to identify worlds that have a similar past as being closer than worlds that have a similar future, but a different past, right? So I don't think that kind of view helps too much. I also don't think that sort of just a conventional interventionist type of approach helps that much, because you know, you need to know what it means to make an intervention on a variable. Okay, in principle, so when you make an intervention in sort of Pearl type causality, what you have to do is you have to disconnect the variable from all of its causal antecedents, and then set it to a particular value in like a do conditional, right? In this kind of approach, when there's potentially retrocausality, everything potentially has a causal antecedent. Like these lambdas can be a causal antecedent of any choice that you make, and we have absolutely no control over them. So there's no possible way of really, you know, breaking any causal relationship that there exists there. So arguably this makes things difficult, right? So I don't think that there's an objective agent-independent notion of causal relation that makes sense in this approach. However, as a matter of fact, there are in the universe entities that regard themselves as decision-making agents. So I am such an entity. I think all of you are such entities. So we can still talk about apparent causality from the perspective of an agent, and arguably that's all we really need for a notion of causality. So I'm going to adopt what I'm calling this subjective interventionist approach to causality. We believe that we can make interventions, right? Whether we're really making interventions or not is difficult to determine from the physics, but we believe that we can make interventions, and based on that, we can come up with a notion of at least what we think is going on with regards to cause and effect. Okay, so this is how this is going to work in more detail. So as a matter of fact, there are variables that we appear to be able to control directly, these red variables, settings on measurement devices and things like that. You know, in a deeper theory of physics, we would like to explain why those are variables that we can control. Okay, so there is an explanation warranted there. It's just at this level, we're not going to provide that explanation, right? It has something to do with thermodynamics, arguably. There are also variables not controlled, but only directly observed, and latent variables. Those are just variables that are neither controlled nor observed, but are correlated with the other variables in any experiment that we do. So we're just going to take it. Okay, so I'm going to say a couple more things first. So the controlled and observed variables, generally we're going to assume can be assigned to small localized regions of space-time. Okay, as decision-making agents, the things that we can do tend to be fairly well localized, right? So the region associated with a controlled variable would be, for instance, the location and point in time at which you made a particular measurement setting, and the region associated with an observed variable would be, you know, the location and time at which the reading first appears on the measurement device. The latent variables, however, may or may not be assignable to small localized regions, okay? So there is this idea of Einstein's separability, or Bell's concept of local beables, that there should be things that exist that are localized in regions of spacetime. So if we have a theory that only has local beables, then of course these things will be assignable to small regions of spacetime. But if we might have more abstract things as our latent variables, in particular, people want to consider theories in which the quantum state is some kind of real latent variable, hidden variable. Quantum states are often assigned to entire space-like hypersurfaces in space-time, or they may be even assigned to completely abstract spaces like Hilbert space or configuration space that don't correspond to a region of space-time at all. However, I will assume that the latent variables, whatever they are, can always be assigned to a region of space-time, possibly not a localized one. This is really no different from what Bell does. He needs to assume that to derive his theorem. If we want something to live in a completely abstract space, then you can always just assign its region to be the entirety of space-time, which really buys you nothing. Okay, so you can always do that without sort of affecting any of the conceptual ideas. Okay, so what I mean by causality here is that a controlled variable is a cause of either an observed or latent variable. So I'm going to talk about a latent variable here, but it could be observed as well. If there exist two different values you can set those things to, that changes the probability distribution of lambda. And I'll just say that there's retrocausality if the region associated with lambda is wholly contained in the backwards light cone of the region associated with x. So here I'm just taking at face value that the controlled variables are things that can be controlled, at least from the agent's perspective. When they set the value of x, it's an intervention. Okay, whether it is really an intervention in the sense of like what's going on fundamentally is really not something that's being discussed here. Okay, so note that from the perspective of a single agent, this notion of causality rules out the no free choice and superdeterminism options, because we're just starting from the agent's own perspective of what they can control. The agent thinks that they can control X, so we're taking that at face value. And so, of course, there is no question of a causal influence on X in that case. But however, this is only from the perspective of a single agent, right? So the reason why this is subjective is that in principle, the notion is agent dependent, right? Because views on what is controllable, views on what you can intervene on may vary from agent to agent, right? So Bob may think that he has control over lambda and he only observes Alice's measurement choice. In which case, in this scenario, Bob would say, okay, I set a value of lambda that affects X, so Alice has no free choice. However, since we're generally in this talk sticking to the perspective of a single agent, it means that everything becomes retrocausality here, right? So I'm sure that this is going to be controversial, but there'll be a discussion of it at the end. But this is basically the framework I'm using to make sense of retrocausality, or the violation of measurement independence. Okay, so moving on, I want to talk about Bell type experiments in detail. So here's the setup again. So we have Alice and Bob's measurement choices and their measurement outcomes. And then the latent variable lambda is going to be the state of affairs in whatever screening off region you deem most appropriate for formulating Bell's theorem. Okay, so there are different people, people make arguments about, where is lambda located in space-time. It's just in a screening off region, whichever one you think is most appropriate, right? Some people take the entire joint past here. Some people take a space-like hypersurface. Doesn't matter from the current perspective, just any screening off region will do. Okay, so what I want to do is go through the assumptions in the conventional modeling of this in a bit of detail, break it down, and then talk about what happens when you drop measurement independence. So the first assumption is that there exists some joint probability distribution over the observed variables and the latent variable given the controlled variables. I call this an ontic extension. This should account for the observed probabilities. So I have a quirk of notation here, which I always do, which sometimes confuses people. When I write prob, I always mean something operational. So prob only ever refers to the predictions of some operational theory, quantum mechanics, say. Whereas PR refers to the predictions of a variable of a theory that includes lambdas, right? So saying that this must account for the observed probabilities, I'm just saying that prob has to equal the marginal of PR over lambda. Okay, right. So that's the first assumption. And then we have the measurement independence assumption, or no retrocausality. In causal model terms, it means that the experiment can be described by a causal diagram, a Bayesian network, if you like, as on the right here. Okay, so basically, none of the arrows in this causal network point backwards along light cones. We can have, at this point, we can have still superluminal influences, but no backwards influences. Okay, and I'm going to use the notation here. This perpendicular notation means the same thing as this. So lambda is probabilistically independent of x and y. And that means that according to this causal diagram, we have this decomposition of probabilities here. Okay, so that's assumption 2. And then assumption 3 is local causality, Bell's local causality assumption, which is now a conditional independence assumption. And this is how I'm going to denote conditional independences. So B is conditionally independent of A and X given Y and lambda. Okay, so this is local causality. And from the perspective of a causal model, this basically means, okay, take this causal model and drop all of the arrows that point in a space-like direction in space-time. Okay, so we end up with this kind of structure for a causal model. Okay, and so this is the assumption that's usually made to derive the Bell inequalities, and this kind of model here cannot reproduce the predictions of quantum mechanics. Okay, so what happens if we just drop assumption 2, no retrocausality? Well, you can see that if you just take this here, I'll just get that lambda can depend on x and y. Okay, and so that's what most authors will say the explanation of the Bell correlation should look like in a theory which has retrocausality or in a theory which has no measurement independence. But to me, this is a little bit suspect because, the way the structure goes is, no retrocausality, first of all, justifies this kind of causal model. And then local causality itself can be thought of as take this causal model and remove some arrows from it, right? So if we don't have the no retrocausality assumption to begin with, we don't have a causal diagram like that to begin with, it's not clear that the same probabilistic assumption can be understood as locality, can be understood because it can't be understood as removing arrows from something that we already had because we haven't made this assumption. Okay, so I think that we need to maintain, so we need to upgrade the assumption. When you remove measurement independence, you need to upgrade the assumption of local causality, because the role of lambda is supposed to be to explain the correlations between the two wings of the experiment. If we allow lambda to just depend on x and y in a completely general way, it's not doing this, because lambda could just contain a copy of x and y, right, and sort of not really be doing anything except containing arbitrary information about the measurement settings. We want to maintain the idea that lambda is mediating the correlations between the two wings of the experiment. So I want to argue like this. So we need a stronger assumption. So what I'm going to do now is specialize. So x and y are supposed to be free choices, right? So Alice and Bob are at liberty to choose them however they like. In general, they'll do that by specifying some joint probability distribution. They'll choose them randomly in some way or another. We're going to specialize to the case where they choose them independently. And also, later on, I'm going to assume that these probability distributions have support on all possible values of x and y. It's not particularly important now, but we'll specialize to that case. Then we're going to derive the structure of the probability distribution. Once we've derived the structure of the probabilities, you can go back to more general ways of choosing. Okay, so the assumption I want to impose is lambda mediation, and this sort of literally says that the two wings of the experiment should be screened off by lambda. So B and Y are conditionally independent of A and X given lambda. Because conditional independence is a symmetric relation, we also get it the other way around. So what I mean by a local block universe ontological model for the Bell experiment is it's an ontic extension that satisfies this lambda mediation assumption. Okay, so first of all, we need to address two things. Okay, so we need to address two questions. Is this a sensible generalization of local causality? So I need to argue that it is. And then if I want to derive what is the structure of a local block universe ontological model, what consequences does it have for how the probabilities decompose? Okay, so I'm going to do some of these derivations. I'm going to use the semi-graphoid axioms. Those of you who are familiar with causal modeling will know these. It just simplifies some of the derivations in this case, right? So that I'm not going to do anything that you can't do directly by looking at the probability distributions. But this is a calculus which, from the perspective of here, from our perspective, is just a calculus of things that are true about the conditional independence relation. And in fact, this is a complete calculus for reasoning about conditional independences. So all of these things you can derive straightforwardly from the definition of conditional independence of a probability distribution. So we have symmetry, which I already referred to. Decomposition says that if X is conditionally independent of two things, Y and W, then it's conditionally independent of them individually. Weak union allows you to take one of these things and put it on the right-hand side of the conditional here. And contraction here, from the probabilistic point of view, has to do with the law of total probability. Okay, and in these axioms, X, Y, Z, and W, they could all be sets of variables, not just a single variable, including the empty set. So I can reason about ordinary independence just by, say, making Z the empty set here. Okay, so that it's from this perspective, it just simplifies the derivations, which are otherwise a little bit messy if you go directly with the probability distributions. Okay, so first of all, I want to answer, is this a good generalization of local causality? Well, first of all, it implies local causality. Okay, so it is a stronger axiom. And then in the context where we do assume measurement independence, it's implied. Okay, so what this result tells us is that it's an assumption which, when we drop measurement independence, includes local causality, but also includes some aspect of the measurement independence assumption that I believe is still appropriate to have in a theory where we have retrocausality. Okay, so proving the first part is easy. It's just an instance of this weak union. We can move something to the right-hand side of the conditional here. Because if I take this and move y to the right-hand side of the conditional, I get local causality. That's very straightforward. The other one is more of a pain. You have to, it takes several steps. So I'm not going to go through the proof in detail because it would just be too confusing, but it's there for completeness if anyone wants to follow it. Okay, so we have that we've specialized the case where x and y are independent. We have the no-retrocausality and or measurement independence and the local causality. And then by a series of steps, you can go from there to lambda mediation. All right, so now we want to know what is the structure, what are the consequences of lambda mediation for the probability distribution. Right, since we've already proved that lambda mediation implies local causality, we know that we can decompose the probability distribution like this, only that we don't have measurement independence. But the point is that lambda mediation now has consequences for this term. It's not just a general lambda given xy anymore. So how do we derive that? Well, okay, so first of all, this is supposed to work for all choices of probability distribution that Alice and Bob might make. And it's very easy to see that if the prior probability for a particular value of lambda is 0, then all of these things have to be 0, and hence the whole probability is 0. So we can specialize, so that's true, and then we can now specialize to the case where we only considering values of lambda for which the probability is non-zero, and that will allow me to use Bayes' rule and divide by it, okay, basically. Okay, so if we start with lambda mediation and then apply decomposition twice, it means that I can delete A and delete B here. It tells me that x and y are conditionally independent given lambda. So what you can then do is take this term and apply Bayes' rule. So Bayes' rule gives me probability of x and y given lambda in terms of, well, like this. And then because of the conditional independence, I can write this as the product of two terms. And now I can apply Bayes' rule again to each of these two terms. That's going to give me all of these probability of x and y's that cancel. And I'll end up with this. Wait, your faces are in the way of the equation. Yeah, so I end up with this structure over here. So now I can plop that back in. And to clean this up a little bit, it's useful to take these two terms and move the lambda to the left-hand side by the definition of conditional probability, because then I can cancel out these two terms. And then I end up with this decomposition. For reasons that will become clear shortly, I've also multiplied it by probability of lambda and divided it by probability of lambda. But it's the same thing that we have up there. Okay, so that is the structure. Except it's wrong because I should have the lambdas on the left-hand side here. Okay, that's a mistake. All right. So note that if my prior probability distribution over lambda is uniform, then this just reduces to the product of these two probability distributions and then renormalized. Okay, and that's usually going to be the case in the model. In the models I'm going to show you in a minute. Okay, so that's what the structure says. Can this reproduce Bell correlations? Well, in order to formulate specific models, it's helpful to generalize this a little bit. So I'm now going to introduce a preparation variable. So the variable P represents the choice of what quantum state you're going to prepare in your Bell experiment, for instance. Okay, so, in an experiment, you may not always prepare the singlet state, but sometimes you can prepare a product state or some other state, etc. So that variable represents that choice. And now I'm going to have, the assumptions will be that all these three are independent. And then I'm going to have the lambda mediation assumption, but now I'm going to have you know, because I've got 3 areas of my experiment, everything has to be screened off by lambda. So P is going to be conditionally independent of these variables and these variables given lambda. A and X is going to be conditionally independent of everything else given lambda, and B and Y is going to be conditionally independent of everything else given lambda. Okay, so you can redo the derivation. That's like, you know, it's more complicated, so I didn't want to make very complicated slides. But basically all that happens is if you go back to this formula, this probability here becomes lambda given P. Okay, so the general formula that you get is now this. And again, if we have uniform prior probability over lambda, then it's just the product of these 3 terms. And it looks exactly like you'd get from in the usual formulation with with measurement independence, except for the fact that these lambdas are now on the left-hand side of the conditional rather than the right-hand side of the conditional. Okay, I'm low on time. So I want to show you that you can reproduce Bell violating correlations in this way. These are like really sort of toy models, not supposed to be taken very seriously, but just to show you how it works. So the simplest kind of model you could do is for the Popescu-Roerlich box. So this is just a set of correlations that violates Bell inequalities more than quantum mechanics does, but it's still no signaling. But it's a sort of a simple model. So here, A, B, X, and Y are all bits. P equals box just means I set up the experiment to produce a PR box, right? And the probabilities are defined in this way, where this plus symbol here means modulo 2 addition. So 1 plus 1 is 0 in that case. And this is ordinary multiplication. So that's the condition. And I've also drawn out the table of values, that have non-zero probabilities. So if X and Y are either 0, 0, 0, 1, or 1, 0, then A and B have to be the same. And if X and Y are both 1, then A and B have to be different. Okay, I'm also going to use this notation here. So the square brackets Z given Fz means the uniform distribution over the values of Z such that Fz, the condition Fz is true. So I can also write this probability distribution like this. Right, so that's the PR box. It violates Bell correlations. And there's a very simple way of, dumb way of modeling this. We just let our latent variable consist of 4 bits. And those are labeled X, Y, and A and B because they're just going to simply hold the values of X, Y, A, and B. And then the probability of lambda, given that you're preparing a PR box, is just the uniform probability distribution over all lambdas that satisfy the PR box condition. And then these 2 probabilities for each of the 2 wings of the experiment, all they really do is copy the values of lambda into X, into X, Y, A, and B. So note that this model is retrocausal because if I marginalize over A here, the probability of lambda given X will be delta X lambda X. So it depends, the probability of lambda depends on the value of X and it depends on the value of Y. So that's where the retrocausality is. Oh, fonts problem. Okay. So we can do the same kind of thing for quantum correlations. So these question marks were supposed to be a curly H for Hilbert space. So you've got to have a state in a tensor product of 2 Hilbert spaces. And for each value that X takes, there's an orthonormal basis of the Hilbert space A. And for each value Y, there's an orthonormal basis to the Hilbert space B. And then the observed correlations are just given by the usual Born rule in mod squared and in products. And then the block universe model for this is going to have our latent variable having 2 lambdas, lambda 1 and lambda 2. Lambda 1 takes values in the set of states that correspond to the measurement outcomes for LS, so all of them, for all the values of X and all the values of A. And similarly for lambda 2. Prior probability distribution is again going to be uniform, and the states will be prepared. So this probability here will just be the Born rule probabilities over our hidden states. And then as before, all that these conditional probabilities do is they copy the right state into lambda. Okay, and that is very straightforward to see that that will reproduce the quantum predictions. So I'm not claiming that these are great models. I'm just trying to demonstrate that you can reproduce the predictions. Okay, so I'm not going to say anything at all about the general formalism, but I just want to mention that it's possible to generalize the lambda mediation assumption to any causal scenario you like. What we have here is, if you imagine, so we have regions of space-time which can hold a controlled variable, or they can hold a controlled variable and an observed variable, and lambdas mediate the correlations, right? So the lambda mediation assumption here would be, for instance, this set of variables here is conditionally independent of everything else given lambda 2, because to get from here to anything else, I have to pass through lambda 2. So you have assumptions like that. It's very similar to what you do in Markov networks and in factor graphs, although it's slightly different from both of them. And then you can prove from that that you get a decomposition where, if I have just a controlled variable in the region, I just get the probabilities of lambdas given, the incident lambdas given that controlled variable. And if I have both controlled and observed variables, then I get a conditional probability of the observed variable and the lambdas that are incident, that are connected by an edge, given the controlled variable divided by the probability of the lambdas on the neighboring vertices. Okay, so that's a general structure that you can get, and it shows that if you have the lambda mediation assumption, then it's not a complete free-for-all. You can't in a general causal structure, you can't reproduce any probabilities you like in this kind of framework. Okay, conclusions. So I've gone a little bit over time, so let me be quick. So we can make sense of causality in the block universe framework in a subjective interventionist sense, right? Whether there's some other notion of causality as well, it doesn't matter too much from the perspective of the framework here, but we can discuss that. When we drop the measurement independence assumption, but still keep the idea that lambda should mediate correlations, we do get a non-trivial structure for the theory. It's not that you can, when you get rid of measurement independence, you can reproduce anything you like. And we can generalize this beyond just the Bell scenario. So further questions, some of which I've worked on and some of which haven't. We want to know, to what extent can you evade the no-go theorems in this framework? So we've already seen that if we regard lambda mediation as the appropriate generalization of locality, then we have local models for Bell correlations in that sense. It's also possible to have models that are time symmetric in the sense of these no-go theorems that was started by Hugh Price, and then a follow-up paper by myself and Matt Pusey. There was a no-go theorem about time symmetry. That one you can get around. There still have to be some kinds of contextuality you can prove. I can discuss that in the discussion if you want. I don't know anything about whether there are psi-epistemic models in this framework. So you have to be a bit careful with this question, because if you look at this model, the state psi that you prepare is not ontic, it's not part of lambda, but quantum mechanics has both a predictive formalism where you evolve states forward in time and a retrodictive formalism where you evolve states backwards in time. And the retrodictive state is real. It's the measurement setting states in this model. Okay, so I wouldn't call that psi-epistemic because the retrodictive state is real. So that's an open question. I haven't really looked through the existing models. So models that violate measurement independence and just talk about superdeterminism or retrocausality in general, how many of those models actually satisfy this lambda mediation requirement? I don't know. I would view that as a requirement for a reasonable theory. And then, of course, we have to explain in terms of this framework. I mean, this is very speculative to think that perhaps there is some kind of thermodynamic explanation we can come up with for why there's no superluminal signaling and backwards in time signaling in this framework. Okay, I'll leave it there. Thank you for your attention.
Thanks so much, Matt. So if we have one or two questions now, we can take them. If they're short questions, then we'll take a break. we're going to have a half-hour discussion period before Eric comes and gives his talk. Again, for those of you who may have joined late, our third speaker, because of time zone issues, will be joining us a little bit later. So instead of at 3 o'clock, Eric will be joining us for his talk at 3:30. So we'll have a discussion period from 3 to 3:30. So let's have a couple of quick questions now if people have them, and then hang on to them, and then we'll have a larger discussion period for questions both for Matt and for Holly. So
before we start, by the way, did Eric arrive yet? Jacob, did Eric arrive?
He is not here yet, no. He's scheduled to be here at
I just wanted to let everyone know that yesterday was Eric's birthday, so wish him happy birthday when you see him.
Thanks for letting us know. I didn't know that. Thanks. Okay. All right. So please raise your hand if you have questions. And I'll also have the chat window open in case people want to put questions in chat. I have a question here from Richard. And Richard, I only have your first name. You're muted.
Richard Healy.
Oh, Richard Healy. It's good to see you. So you're also your image is also not on my current gallery view, so I couldn't see your face.
Should be now.
I can see you now. Great. Good to see you. Go for it.
Yeah, I'd just like to follow up on your point that there is still contextuality in the models you were talking about. Can you elaborate on that a little bit?
Well, I'm talking about, so, I mean, it's kind of like easy to see why there is some kind of contextuality. So I'm talking about in the generalized sense of Rob Speckens, right? So there you say, okay, if you have two operationally equivalent procedures, then the description of them in the underlying model should be the same. And so it's really easy to see that if you have any retrocausality at all, you immediately have a type of contextuality, because here are two things that are operationally equivalent. Make measurement A and then throw the system away. Make measurement B and then throw the system away. Like, don't record the measurement outcome, just throw it away. Those are operationally equivalent.
Right.
You know, the thing only has one outcome. But if there's retrocausality, then there's information in the ontic state about whether you measured A or B. Right. Mm-hmm. So there has to be, because otherwise there'd be no retrocausality. Right. So any model for the Bell experiments that's local, of course, is going to be retrocausal and hence contextual in that sense. However, what's not clear is that every single proof of contextuality that applies in the standard framework works here. So there may be some kinds of contextuality that are present in standard ontological models that aren't present here. And I suspect that's true in the case of things like the Perez-Mermin square, because that kind of contextuality, I mean, I haven't worked out, I'm trying to work out the details of a model which handles what's called stabilizer quantum mechanics. And I believe it's true that you can have a appropriately non-contextual model for stabilizer quantum mechanics in this framework, but just not all. So that's a type of contextuality that I don't think you need in this framework, but there are types that you definitely have to have.
Thank you.
Great. It's 2:55. So if anyone has additional questions, please hang on to them for 5 minutes so we can take a break, and then we'll bring them all back again at 3 o'clock for a half-hour general discussion. So let's all take a 5-minute break. But I want to thank Matt again for a wonderful talk before we take a break. Thanks again, Matt.
Thank you.